Another really exciting project that you've been involved with at Meta AI is evolutionary scale modeling, ESM protein models. And I think we should also, something maybe to acknowledge right away with these kinds of, over the course of this episode, we're going to cover so many different topic areas. So maybe is there some way that you can kind of orient us to the body of research that you've contributed to? Is there a common thread? I mean, is it just machine learning and you're just like, what is the coolest thing I can do with machine learning right now? And then you end up having all these different kinds of disparate projects?
Yeah, I mean, I do always like projects where you like try to build something and where you try to bring a step change in sort of the capabilities that we have, right? And so, in terms of like risk, like I always want to be sort of on the high risk part of the spectrum. Like I'd rather fail miserably than not try at all, which is sort of a choice, right? Like other people are going to be somewhere else on the spectrum. And so I'd say that is sort of the main thing, like let's really build things. I think that is what motivates me. And sort of thinking about like at a high level, what is wrong with, or like what is missing sort of in current approaches that we could change. And so ESM project, I think, is a really cool example. You should get someone from the team on your show at some point, like someone like Alex Reeves, would be a really exciting person, I think, to have on the podcast.
Sounds great.
The basic idea of this project is trying to do de novo protein design. So trying to do design of proteins that are unlike anything that exists in nature. And sort of the way that the team is going about that project is by taking a somewhat similar approach, by doing essentially language modeling on really large data sets of proteins. So proteins are really just sequences of amino acids. There are about 20 amino acids. And so like it's really a sequence of like tokens, and each token can have 20 values. It's gotten really easy to get those sequences, right? Like sequencing proteins has become really cheap. And so there are publicly available databases with hundreds of millions of proteins that were sequenced. And so what you can do is you can train language models on that. And those language models develop a representation of protein that captures, something about sort of the structure of those proteins. And you can use that representation to sort of condition folding algorithms on. And that's exactly what the team did. And so what is folding about? Folding is basically, like you have this sequence of amino acids, but really what you care about is sort of what is the shape of this protein. This protein sort of like starts folding in all sorts of funky ways. And those sort of the way sort of the 3D structure of the protein is lined up determines sort of what function does it have. So like what does it actually do? And so what you want to predict is like, what is the 3D structure of this protein given this amino acid sequence? Because the 3D structure is really expensive to get. It's only the sequence that you can get cheaply. And so what the team did is they conditioned folding algorithms on these language modeling representations. And so what they were able to do is to deliver folding sort of prediction results of the same quality as AlphaFold 2, but without homologs. So AlphaFold 2 requires you to specify sort of like, well, I want to fold this protein, and here are some other proteins that are like kind of similar to the one I want to fold. So those are called homologs. And the folding algorithm that the ESM team developed doesn't require these homologs. And that is important if you want to do de novo design, right? Like if you want to design completely new things, then there is nothing, right? Like there are no sort of comparable proteins that you could use as homologs to sort of condition your folding on. And so it's really a stepping stone towards doing that type of protein design.
That's really fascinating. And it is something that we've talked about on the episode a few times this year. So we had in episode number 643 at the beginning of the year, we had Professor Charlotte Dean, who's an Oxford University professor.
Awesome.
Do you know her? You kind of.
I don't.
Oh yeah, you nodded so much that I was like, oh, it's going to turn out that he knows her too. But her research is focused on this protein folding kind of problem as well. And she, at the time of recording, she'd been having dinner with Demis Hassabis the night before. And so she was also talking. So while AlphaFold 2 has the biggest name recognition in this space in terms of protein folding, it is specialized, as you say, to this specific problem. I guess when you have homologs, I wasn't aware of that detail. But for dealing with this particular folding challenge, whereas Charlotte Dean was describing that for some kinds of proteins, there's complexities that kind of AlphaFold 2 modeling doesn't work for. So in her case, I think it was hemoglobin binding, or maybe it was binding structures in general. And there's so much variability in what proteins, in how they need to be configured to be able to bind to all different kinds of objects in the body, antigens in the body, I guess. And because, as you're saying, to create these data sets, to actually know what the 3D structure is very expensive, that there's still a lot of unsolved problems there. And so it's interesting that you at Meta AI with this ESM protein project have been able to do these predictions without the homologs and be able to predict protein structures that we've never seen in nature before. Is there when you create these de novo proteins, is there some kind of purpose deliberately in mind?
No, nothing specific. Sort of right now, like the use cases of this could be very diverse, from like drug discovery to design of enzymes that compost plastics faster. So it can be sort of like all over the place. Mostly, I guess, sort of like in medical applications, right? Like that's where you'd sort of have most sort of potential use cases of this work. But we're just using it as a sort of test case to build up sort of our experience in things like language modeling and so on, right? And like have different use cases for the same technology, so that sort of the underlying technology that we're developing becomes more robust.